Greetings. The title of my talk, Contextuality as Extension of Selective Influences. Let me begin with the way one usually introduces the problem of selective influences. There are two stimulus properties or aspects, or simply two stimuli, X and Y, and a person, animal, or gadget is responding to X and responding to Y. X and Y can change, assume different values, and combine in different ways. It is possible, of course, that the response to X is also influenced by Y and or vice versa. How can one define the notion of a response being selectively influenced by a given stimulus property? Let us consider the simplest factorial design in which X and Y can attain two values each, encoded here by 0 and 1, with all four treatments possible. Response to X is denoted by capital A, response to Y is denoted by capital B. A and B are random variables, and I will assume they are dichotomous random variables, each with two possible values. Generally, the random variable A depends on both X and Y, because of which I here attach the values of X and Y to A as its superscript. So, A01 means that A is responding to X equals 0, the first superscript, while Y is at value 1, the second superscript. Analogously for B, responding to the second superscript. Clearly, to speak of selective influences, one should expect that the distribution of A only depends on the value of X. For example, A00 and A01 should be distributed identically. Analogously for B, these random variables are identically distributed. Such identity of distributions, if it holds for all pairs of variables responding to the same stimulus property, is called marginal selectivity. But this is only a necessary condition for selective influences. Here is the definition of selective influences in a 2x2 system, assuming that marginal selectivity holds. Such a system is called non-contextual, and for now, we will take this term simply as a synonym for selective influences. The definition is that a 2x2 system satisfying marginal selectivity is non-contextual if one can find functions f and g and a random variable lambda, such that when f and g are applied to the random variable lambda and certain values of x and y, one gets a pair of random variables that is distributed as the AB pair at the same values of x and y. In addition, we require that the values of f does not change when y changes from 0 to 1. Analogously, the value of g should not change with x. One may wonder whether this definition is constructive at all. Can we find these functions f, g, and the random variable lambda, and if they do not exist, can we determine that they do not exist? The answers are yes, and quite easily too. The functions f and g at specific values of x and y are just dichotomous random variables, and since they are all functions of one and the same random variable lambda, they are all jointly distributed. In each row of this matrix, the pair of f and g forms a distributional copy of the flanking a and b. So, we denote these random variables in each row by a bar and b bar with the same superscript as the flanking a and b. We need to assign probabilities to all possible values of this octuple of a bars and b bars, so that these two random variables always have the same value, and the same is true for these, and these pairs of random variables. For many particular cases, including this one, the 2x2 system, there is a closed form expression whose value determines whether a solution exists. But more generally, this is a simple linear programming task, and if a solution exists, it doesn't have to be unique, by the way, then the most economic choice of lambda is simply the octuple of the a bar and b bar variables, while the functions f and g are simply projection functions. If the linear programming problem has no solution, then we say that the system is contextual. And the interpretation of contextuality here is that although the distributions of the a's in this pair are the same, and the distributions of the b's in this pair are the same, at least in some of these pairs, the random variables cannot be treated as being the same. I assume we all understand clearly the difference between a random variable and its distribution. The notion of selective influences was introduced to psychology by Saul Sternberg in this famous paper. It was applied to the problem of mental architectures, where the responses A and B are durations of processes that are not directly observable. One can only infer them from their contribution to an overall hypothetical processing network. In the ensuing years and decades, the notion of selective influences was elaborated by these gentlemen, among others. This talk is based on the solution for the problem of selective influences proposed in this paper. The mathematics and applications of the notion are summarized in this chapter in the new Handbook of Mathematical Psychology. Let us return, however, to the 2x2 factorial design and consider it in the situations when the responses A and B are directly observable. For instance, X may be intensity level of light, Y the shape of the aperture, A may be a judgment of brightness, say dim versus less dim, B a judgment of shape, say circular versus slightly oval. The classical problem associated with such a design is the problem of perceptual separability versus perceptual integrality. Is intensity processed separately from shape, or is their processing inseparable? Several approaches have been proposed, among them Roger Shepard's approach based on multidimensional scaling, general recognition theories approach by Jim Townsend, Greg Ashby, and others, as well as my and Hans Colonius's approach based on generalized Fechnerian scaling. One might think, however, that the most natural approach to the problem of separability versus integrality would be to use the notion of selective influences. If light intensity selectively influences judgments of brightness and aperture shape selectively influences judgments of shape, then and only then we have separability. Why hasn't been this most obvious approach used? The reason is that in all factorial experiments known to me, if there are two directly observed responses to two stimulus properties, marginal selectivity never holds. As a rule, these random variables will be differently distributed, and so will be these two, and so on. It looks like we have hit a dead end. We always deal with a picture like this, with direct cross influences, precluding, therefore, selective influences. However, the notion of contextuality turns out to be more resilient than that of selective influences. It can be generalized to situations when marginal selectivity is violated. Here is the definition. The beginning is the same as before. The 2x2 system is non-contextual if one can find functions fg and a random variable lambda such that this pair of random variables is distributed as the AB pair at the same values of x and y. In addition, however, and here lies the generalization, we require that the value of f change as little as possible in response to y, so this equality is preserved not always, but with the maximal possible probability. Analogously, the value of g should change as little as possible in response to x in the same sense. If marginal selectivity holds, this maximal probability is 1, and we have the previous definition as a special case. If marginal selectivity does not hold, this maximal probability is less than 1, and always readily computable. Once again, the functions f, g, and the random variable lambda can be found constructively by means of linear programming. Using the same logic as before, we have to assign probabilities to possible values of this octuple of random variables, such that the probability of these two random variables being equal is maximal, and the same for these, and these ones. We face here a more general linear programming problem than before, but not too different. If no solution exists, the linear programming will determine this, and then the system is said to be contextual. The interpretation here, and the general interpretation of contextuality, is that in some of such pairs, the difference between the random variables is greater than the difference of their distributions. Contextuality or non-contextuality of a system is not just a binary classification of systems. Contextuality can have different degrees, and here we can see our system represented by a probability vector P and a polytope containing all non-contextual systems. To depict our 2x2 system, we need a 4-dimensional picture. So what you see is a 2-dimensional analog or projection. The distance here is L1 distance, not Euclidean one. The degree of non-contextuality also can be measured as the L1 distance, this time from an interior probability vector P representing the non-contextual system to the surface of the non-contextuality polytope. It can be like this or like this, but we will not be getting into details. What is important for our discussion is that we have now a conceptual apparatus to handle the separability versus integrality problem, even when marginal selectivity is violated, when we have direct cross-influences. And we can do this almost as the unrealizable intuition of selective influences suggested doing it. We can determine if the system is non-contextual, and if it is, we can measure the degree of its non-contextuality and interpret it as the degree of contextual separability. If the system is contextual, we can measure the degree of its contextuality and interpret it as the degree of contextual integrality. The contextual separability and integrality characterize a system in addition to any direct cross-influences. It is straightforward to measure the degree of the direct cross-influences. I did not discuss this and will leave it undiscussed for the lack of time. Of course, separability integrality of perceptual tasks is not the only advantage offered by the notion of contextuality and non-contextuality. Unlike the notion of selective influences, contextuality and non-contextuality applies to designs very different from the factorial one I considered in this talk. If interested, you can find the theory and applications of the contextuality analysis in these papers. That's all.